We're going to be looking at the chemistry of alkenes. There is a reaction mechanism in this, and there is also a bit that gets overlooked, which is polymerization. Okay? People forget about polymerization because it's in the GCSE materials. I don't have the ability to draw on this board without really annoying people. Okay, so with the mechanism stuff, we might have to revisit that later. This is what we're going to be going through. We're going to start off with things that you know about, which is the structure of alkenes. We're then going to look at naming them, isomerism, physical properties, and then electrophilic addition reactions. That's the mechanism that we're going to be covering this morning. So, before we start, I was talking about this morning with a pupil. Definition of a covalent bond, please. What is it? Yeah.
Bond where two atoms are similar in electrons.
Okay, very simply, what is a covalent bond?
A bond where electrons are shared.
Be more specific.
A pair of shared electrons.
A pair of shared electrons. That's all you had to put. A covalent bond is a pair of shared electrons. Understand the difference between homolytic and heterolytic fission. We covered this last week. What is the difference between those two?
When the bond breaks, the electrons conjugate on the atom that is catalytic, molecules become little conjugate to electrons.
Good. If the two electrons go in different directions, that's homolytic fission, because it's split up equally. If the two electrons go to one side, that is heterolytic fission, okay, because it's split up unevenly. You can balance simple equations, be able to write out structures for hydrocarbons. I'm pretty sure you can do that. Recall the chemical and physical properties of alkanes. Alkanes are pretty unreactive, apart from the fact they burn very well. Okay? Chemically, they do very little, because they're very stable. So, do we remember, hydrocarbons contain only carbon and hydrogen. Okay? It's not, you can't just say they contain carbon and hydrogen, you have to say they contain carbon and hydrogen only. General formula for an alkene is CnH2n. Hello? Just pause it for a second, please. Right. Formula is CnH2n. I want to flag at this point that this is also the formula for cyclic alkanes. Okay? For alkanes that go around in a ring. And you need to realise that something can have the formula of, say, C6H12. C6H12 is either cyclohexane or it's hexene. Okay? And one common way to distinguish between the two, back to GCSE, bromine water. Okay? Bromine water will not react with cyclohexane, but it will react with hexene. Got it? So, they are unsaturated, you should know that, and they contain a carbon double bond. And all of their chemistry is based around the carbon double bond. You should know that the bond angles are about 120 degrees, and that the carbon double bond is planar. Okay, so all of this structure here, this whole area here, is in one flat plane. Happy with that? Yep? Okay, we're not going to be considering hybridization of orbitals. We're going to skip through that, and that, and that. What we should, however, consider is the structure of the double bond. If you consider a carbon atom to have the different orbitals, okay, these ones here, these are effectively your s orbitals, okay, and it's a little bit more complicated than that because they're sp hybrids, okay, but these bonds here and this bond here, this is a sigma bond made by overlapping s orbitals. Is that okay? S orbital overlap gives you a sigma bond. Sigma, S-I-G-M-A. Okay? However, that then leaves the pi orbitals here. And what can happen is those pi orbitals can overlap. And what you end up with is the double bond being pi orbital overlap, p orbital overlap, forming a pi bond. So let me run through that again. When your s orbitals overlap, you get a sigma bond. We okay with that? S orbitals, sigma bond. When your p orbitals overlap, you get a pi bond. Happy with that? Yep. Now, importantly, this orbital is above and below the plane of the rest of the molecule. Okay? And, although you can't really see it on the diagram here, this does not come out in front of the molecule. This is just above and below. Okay? Now, crucially, what that means is that the bond can't rotate. This end can't rotate with respect to that end. Am I losing you? No? Yes? Little bit. Okay. S orbital, sigma bond. Are we happy with that? And what can happen is that one end can rotate round with respect to the other. Okay, something like ethane, okay, CH3 at one end can rotate round with respect to the other end. You happy with that? Whereas, with the pi bond, so here's, my lightsaber is now representing a sigma bond. Happy with that? With the p orbital's here, and here, here, and here. Happy with that? And these overlap there, and they overlap there. Happy with that? And what that means is that the two ends can't rotate with respect to each other. Does that make sense? Yep, seeing some nods. As an aside, what does that mean? We'll come to that later. It gives rise to a form of isomerism. Okay? Just as an aside, if you were to have a carbon triple bond, you'd have your sigma bond there, you'd have your pi bond there, and then you'd have a second pi bond in front and behind. Okay? We'll come to why it's important in a little bit. So, here we have p orbitals, your p orbital overlap, and then your pi bond. We all good? Yep. Okay. Naming alkenes. You should now be happy with naming alkenes. This molecule down here is 5-methyl X2E, and it's numbered 1, 2, 3, 4, 5, 6. Okay, so you've got a methyl on the 5 and you've got the ene on the 2. Okay? The double bond goes between carbons 2 and 3, and so we choose a smaller number. Remember, we always choose a smaller number, so that's carbon 2. Happy with that? Okay. We're going to go through two types of isomerism. Firstly, structural isomerism, and secondly, geometrical isomerism. I think you should all be happy with these three isomers. Pen-1-ene, pen-2-ene, and 3-methyl-but-1-ene. Okay? But I just want to consider the different bits for them. These two are structural isomers of each other. Okay? Sometimes known as a subset of that, position isomers. You've got the same basic chain, but the bond is in a different place. These two positional isomers of each other. You happy with that? These two are chain isomers of each other. The double bond is in the same place, but then what happens down the rest of the chain is different. Does that make sense? Yep. Chain isomers of each other. Okay. These two, however, are something quite different. If you just had a single bond here, okay, and a single bond here, what could happen is the right-hand side of this molecule could rotate round, and you'd end up with that molecule. But, as I made very clear earlier, the alkene double bond can't rotate. Okay? Which means that these two here, these two sides are locked, and that this molecule is not the same as that molecule. Are you happy with that? Crucially, these two are geometric isomers of each other. And the type of isomerism shown between these two molecules is geometric isomerism. Anywhere you see the words geometric isomers in AS chemistry, double bond. Anywhere you have a double bond, geometric isomerism. Okay? Happy with that? Right. If these are chlorines here, this is 1,2-dichloroethene. Happy with that? And this is 1,2-dichloroethene. But they're not the same molecule. So we have to have some more advanced naming system. Okay? Now, you will see two different naming systems used. First naming system. This is the one that I learned at school, and you'll still see in a lot of textbooks, but unfortunately it's not what the syllabus now requires. Cis and trans. Trans means across, and these two are across the double bond, like that. You happy with that? No idea what cis stands for, but I always remembered it as C-shaped. Yep. Am I losing you, or are you okay? What we basically have is the heavier, or the functional group here, are on the same side of the molecule, and here they are across the molecule. Happy chappies? Right. Except we don't use that notation anymore. Okay, we use notation based in the German language. So this is Z, and this is E. Okay, and that's what you do have to remember. Now, there are two ways of remembering this. Okay? First way is you would expect Z to be a Z shape, wouldn't you? Yep. So you have to remember that Z is not Z shaped. Is one way of remembering it. It's a bit confusing, isn't it? The other way, and this is even worse, okay, is said with a phony fake German accent, same side. Okay? The Z, same side. Anybody wants to come up with a better way of naming them or remembering them, that's fine. Otherwise, remember that Z is same side. That's bad, isn't it? Yep. Okay. But, excuse me, this is important. Here, the functional groups are on the same side, that is Z. Here, they are on different sides, and that is E. Happy with that? Right. Here's the words they're taken from. Z is zusammen, and E is integrated, something like that. It is a slightly more complicated naming method than cis-trans, and you can do it for more complicated molecules. The basic thing you have to remember, right, is it works on the basis of which is the heaviest molecule, which is the heaviest functional group. Okay? And how do the heaviest functional group on one side relate to the heaviest functional group on the other side? Does that make any sense? So if I go back a slide, chlorine is heavier than hydrogen, yes? Chlorine is heavier than hydrogen. So we have the two heaviest groups that are on the same side. Whereas here, chlorine's heavier than hydrogen, chlorine's heavier than hydrogen. So we have the two heaviest groups on opposite sides. You happy with that? Now it's slightly more complicated than that, and I really think it's unlikely you're going to get anything more complicated in the syllabus. But what I want you to realise is that this one here, what do we reckon? E or Z? I reckon this one. I reckon this one's E, because of hydrogen and methyl, methyl's the heaviest. And of methyl and ethyl, ethyl is the heaviest. You happy with that? Okay, pause it for a second, please. Going back to this molecule, methyl hydrogen, methyl's heavier. Methyl ethyl, ethyl's heavier. The two heaviest groups are across the bond like that. Therefore, it is E. This one here, H methyl, that's heavier. Ethyl methyl, same side, Z, same side. This one here, chlorine hydrogen, methyl hydrogen, Z. Here, E. Getting the hang of it. And it turns out I was right. Good. Cis-trans, exactly the same as we've already talked about. I'm not going through that again. Okay. Here we have a nice little diagram showing ethane with one end rotating relative to the other end. Okay? Doesn't happen with a double bond. Okay? It can wobble, it can vibrate, but it can't rotate. You happy with that? Importantly, you have to have two different functional groups on each side of the double bond. So here, two different functional groups, geometric isomerism. Here, functional groups are the same, no geometric isomerism. Here, functional groups are different, so we're all good so far. Here, they're the same, no geometric isomerism. Here, lots of different functional groups, geometric isomerism. Are you happy with that? Yeah? So, butene, okay, but1-ene, does that display geometric isomerism? No. Two groups the same. But2-ene, however, does. It's got same side, and it's got E. And finally, we've got 2-methylpropene. These are all isomers of C4H8. But these two are geometric isomers. Whereas these two are chain isomers. And these two are position isomers. Position, chain, geometric. Got it? No? Okay? Are you happy that this one, you've got a 1-ene? Yep. And this one is also a 1-ene. Okay? But they've got different arrangements of the chain after that. So these two here are chain isomers of each other. Got it? These two here are position isomers of each other. Same chain, functional group in a different place. So those two are position isomers of each other. Whereas these two here are both but2-ene, but they're geometric isomers of each other, because one is Z and one is E. Now you happy? Good. Physical properties. Boiling point. Bigger the molecule, higher the boiling point, because the bigger the molecule, the more electrons, the greater the van der Waals forces. Okay, branch chain ones, slightly lower boiling point than straight chain ones, because the molecules don't line up as well in the branch chain ones. Melting points, nice straightforward thing. Alkenes are non-polar, so they don't dissolve in water. Water would dissolve pretty much anything that's polar. Okay? Alkenes are non-polar, don't dissolve in water. But they will dissolve in most organic solvents. Right. Oh no. Mechanism warning. Okay? Mechanisms are pretty much guaranteed to come up. Because there are only 4 of them, and they're all going to come up. Okay? For the past few years, since they've cut down the syllabus to reduce the number of mechanisms available, Okay? They have then examined each mechanism every exam. So, it's alright, mechanisms are easy. Once you get your head around them, they're easy. What were my 2 rules from last week? What were the 2 rules for mechanism? That was the second rule.
Always charge something.
Yeah, identify the positive and negative. Negative goes to positive. Okay? So, here we have a polar molecule. Delta plus, delta minus, and here we have lots of electron density. Happy with that? Negative goes to positive. Is this negative going to attack anything on here? No. But this negative here can attack that. Yes? So the negative is going to attack that, at which point this little chappy here is going to nick all the electrons from there. Okay? So the electron's going to go from there to there, form a bond there, and then from there into there, which is exactly what happens. Double bond breaks, goes to the positive part, the electrons from the covalent bond are then released to the electronegative element here, because it's going, I want all the pi's. Okay? And at which point it gets them all. Now, importantly, here we're losing a pair of electrons, which means this carbon here, it's not fussed because it forms the bond, so it effectively keeps them. The electrons were there, they moved around and are now there. But this carbon here, this is now an unhappy carbon. It's lost its electrons. Okay, it's now positive. And this is called a carbocation. Carbon positive ion. You happy with that? Carbocation. Then, of course, this little chap, it's nicked all the electrons. It's now negative. It's negative, that's positive. What was rule number 2? Negative goes to the positive. Electrons, whoop, into there, boom, your molecule. Right. What is it that this molecule here liked about that molecule there? It's electrons. Okay? If it likes this the electrons in this, it is an electrophile. It's an electrophile. Excuse me? And this has been added to that. Ergo, electrophilic addition. Got it? Good. Another example, well, specific example, HBr. Okay? Out go the electrons, onto there, the electrons go onto there, the electrons go back to there, boom, bromoethane. Just sort of talking you through it, I've already done that, and so on. Little animated mechanism. Out come the electrons, join onto the hydrogen. Electrons go to the bromine, and you get, what did I call this? Carbocation. In go the electrons, and you get HBr added to the alkene. Now, bromine does exactly the same thing. Do you remember the test for an alkene? Decolorization of bromine water? Well, here's the mechanism for it. In comes the Br2. But hang on a minute, Br2 it doesn't have delta positive and delta negative. The thing is, as it comes in, its electrons are going to be repelled by the electron density from the double bond. So this end becomes slightly positive, that end becomes slightly negative. Voila! Exactly the same thing happens. Happy with that? More diagrams explaining what I just explained. Electrophilic addition of bromine, test for unsaturation. Okay. Place a solution of bromine in the test tube, add the hydrocarbon to the top, shake it. If it goes colourless, it is an alkene. We're not going to worry about that. We're not going to worry. Actually, very quickly. No, we're not going to worry about that. Last major little bit on this. Just pause it for a second. Right. With propene, it gets a bit more complicated. Okay? There are two possibilities. Here's propene. Bond can break, hydrogen go on the end, bromine can go in the middle, and we get, name of this molecule? This is bromine. What is it? What's this molecule here? Come on lads, this is not rocket science. What is the name of this molecule here? Say again? 2-bromo propane. Thank you. 2-bromo propane. But there's a problem. This can happen as well, where the bond breaks the other way and the bromine gets added to this end. And that gives us 1-bromopropane. I'm going to give you the short version on this. The short version is that this one happens much more than this one. This one here is a secondary carbocation. Now, carbocations are very unstable things. They're very unhappy things. They react very quickly. The thing is, a secondary carbocation, and this is what you have to remember, all right, this is your phrase to get the mark. A secondary carbocation is more stable than a primary carbocation. Now, what that means is it survives long enough to react. A primary carbocation is unlikely to be formed in the first place because they're so reactive, okay, that they'll just go back to what they were to begin with. Whereas a secondary carbocation is more stable and survives long enough to react. Does that make sense? Yep. So a secondary carbocation is more stable than a primary carbocation, and a molecule formed with a secondary carbocation intermediate is more likely to be formed than a molecule with a primary carbocation intermediate. Somebody wake him up, please. Thank you. Sorry, you were looking as though you were head down, eyes closed. All right, apologies. Thank you. We're not going to do Markovnikov's rule. And we're not going to do that. We're not going to do that. And we're going to turn to here. Right, I'm just going to blitz through this bit. You can react water with it. We can't react water with it. You can react steam with it. Nice and quiet, please. And you can form ethanol. Okay? Sorry, can you pause a second, please? Right. Steam can be added to ethene to make ethanol. This is a high pressure, high temperature environment, phosphoric acid catalyst, and you get that. And that is one way of making ethanol. The other common way of making ethanol is via fermentation. This process relies on fossil fuels, it's high energy, you get very high yield, and it's very pure. Whereas fermentation, renewable process, okay, but you get very low yields comparatively, and an impure product. You can react it with hydrogen over a nickel catalyst to get ethane. Uses: margarine manufacture. Okay? You don't make margarine out of ethene, but as was covered in the GCSE syllabus, if you have an unsaturated fat, okay, like vegetable oil, you can add hydrogen to the double bond and you can saturate it. And you can partially saturate it, and this increases, okay, the boiling point, the melting point. Okay? By removing the double bonds, you allow the chains to line up more evenly, the melting point increases, and vegetable oil goes from being a liquid to being a solid at room temperature. Okay. Polymerization. For some reason, pupils always forget this from GCSE. If you start off with ethene, you make polythene. And that's all very straightforward. These are the repeating units. Ethene goes to polyethene. Propene goes to polypropene or polypropylene. Chloroethene goes to polychloroethene, otherwise known as polyvinyl chloride. And finally, tetrafluoroethene goes to polytetrafluoroethene, common name, Teflon. Okay? These here are the repeating units. It shows the minimum block that if you repeat multiple times is the molecule that you get. Now I've gone over that very, very fast, but you should all know that, regardless of GCSE syllabus, from year 11. I'm seeing some raised eyebrows though at this point. Are you happy with this? Okay. We're not going to worry about that. Problems with polymers. Recycling them. Lots of different polymers, hard to recycle because they're hard to separate. Okay. However, addition polymers are non-biodegradable. So, they survive in landfill for a very, very long time. If you burn them, you get HCl given off, and so on. They can, however, be broken down to be turned into new hydrocarbons. But that's quite a lot of effort. We're not going to worry about that. And there we go. Okay, can you pause please?